So again, hello and welcome to this 20th edition of our virtual seminar on precision physics and fundamental symmetries. Today we will have our first shared contribution by Jeroen Koelemeij from the Free University of Amsterdam and Jean-Philippe Karr from LKB in Paris. And they will be talking about experimental and theoretical studies of molecular hydrogen ions in the low parts per trillion range, Doppler-free laser spectroscopy, QED, and the values of physical constants. So let me quickly introduce our two speakers. Jeroen obtained his PhD in 2004 in laser cooling and trapping of atoms. Afterwards, he spent time at LKB in Paris, NIST in Boulder, and in the group of Stefan Schilder, Heinrich Heine University in Düsseldorf, specializing in optical clocks and precision measurements on trapped molecular ions. In 2008, he founded his own research group at the University of Amsterdam, where he has focused on high precision studies of molecular hydrogen ions in fiber optic time and frequency transfer. Between 2014 and 2019, he was also co-founder and chief technology officer of a spin-off company which provides time and frequency distribution technology for telecom networks. In 2019, he moved then back to a full academic position at the University of Amsterdam. And let me also welcome Jean-Philippe Karr, who obtained his PhD in 2001, where he studied quantum optical effects in semiconductor microcavities. In 2002, he got an academic position at the University of Évry and joined the trapped ion group at LKB in Paris. He then started working on precision spectroscopy of hydrogen molecular ions. In recent years, he has been focusing on the theory of these systems. So welcome both, Jeroen and Jean-Philippe. Thanks very much for agreeing to give a talk in this seminar, and I leave now the audience to you.
Well, thank you, Stefan. Thank you also for organizing this series of seminars. Personally, I've been enjoying it a lot. And I'm also very happy to have this opportunity to talk about our research. And I will be talking today about results that we obtained by well, experimental studies and theoretical studies on the molecular hydrogen ion. And I will be addressing the experimental side of things. And Jean-Philippe will be talking about the QED and the theory part of these studies. And we like molecular hydrogen ions. And the reason for that is that they are molecules, and they have features that you do not find in atoms. For example, rotations and vibrations. And if you look at the Hd plus molecule shown here, that consists of a proton, a deuteron, and an electron, then, well, it doesn't take much imagination to realize that these vibrational energies and rotational energies are directly dependent on the proton electron mass ratio and the deuteron electron mass ratio. And these are quite fundamental quantities in nature. Another interesting aspect of the molecular hydrogen ions is that they are simple three-body systems. So they are very accessible to theory, and they're simpler actually than most atoms. And Jean-Philippe will give more information about how to apply, for example, QED to these molecular systems. Now, in Amsterdam, we have an ion trap experiment where we do measurements that we compare with theory. So we basically do tests of fundamental physical laws. We also do some searches for potential new physics. So in a way, you can consider this as a tabletop complement to the big particle accelerator experiments like at CERN. Though I must admit that the old dye laser system that we used to have requires probably more maintenance than the entire ATLAS detector, unfortunately. Now, what we like about theory is that it can predict the value of observables. And that could be, for example, a vibrational transition frequency in the Hd plus molecular ion, or it could be an electron G factor or a lamp shift in an atom. And the observable, that is something that we can compare with our measurement. Now, theory doesn't produce that number all by itself. You need to specify some input parameters, the physical constants, And well, then we can do an experiment. The theory can do can predict the value of the observable, and we can compare the two. And this is interesting by itself, because the question always is, do you find agreement also at the next digit of precision and at the next level of complexity, going from particles to atoms to molecules? Now, if you find agreement, that's great, because it gives us additional confidence in our theoretical framework. We can also rule out certain types of new physics. And if they don't agree, then, well, you may wonder whether you're witnessing a breakdown of the existing theory, or whether you're perhaps looking at some overlooked experimental or theoretical aspects. You can also do things the other way around. Then we provide the value of the observable by measurement, and you apply theory in the backwards direction to derive new values of the physical constants. And this is, for example, what CODATA does for many of the constants that they determine. And there has been this idea around since 1976. It's an idea by William Wing and Willis Lamb to do precise spectroscopy of vibrational transitions in HD+, and then use accurate theory to translate these frequencies to a new value of the proton-electron mass ratio. And it actually took 4 decades before that could really be implemented. And that is to a large part thanks to these 3 gentlemen, Jean-Philippe Karr, Laurent Hidiko, and Vladimir Korobov, who have for 15 to 20 years been working very hard on improving the precision of the theory, the ab initio theory that describes the rotational vibrational level energies in HD+. And they have achieved a very impressive improvement by more than 2 orders of magnitude, with the current precision being at the 8 parts per trillion level or so. And what's even more impressive is that currently the theory is so precise that the precision of the predictions that they make on the observables is not limited by the theory anymore, but by the uncertainties of the fundamental constants that they use in their calculations. Now it's up to us experimentalists to match the theoretical precision with experimental precision. And this is something that we try to do by doing laser spectroscopy of vibrational transitions in molecular hydrogen ions. And what you see here is a graph showing the electronic ground state potential, which binds the proton to the deuteron. And this potential supports vibrations of the nuclei. And you can excite the vibration with a laser, like shown here between this vehicle 0 vibrational state to this vehicle's 8 vibrational state. And this is a transition that we studied and reported on a couple of years ago. And the interesting thing about these transitions is that they have a very narrow natural line width on the order of 10 Hertz. So you could, in principle, achieve a very high resolution. Yet you need to overcome things like Doppler broadening, pressure broadening, and that leads you to the idea of using ion traps, because we know that laser spectroscopy and ion traps can be done at very, very high precision. And in fact, today's best atomic clocks are based on ion traps and laser spectroscopy. Now, a lot of the groundwork for the techniques that also we use in our experiments was done in the group of Stefan Schiller in Düsseldorf, where they showed for the first time that you can actually trap and sympathetically cool molecular hydrogen ions together with laser-cooled beryllium ions. They demonstrated the first vibrational laser excitation of HD+ and detection by resonance-enhanced multiphoton dissociation. And the first complete spectroscopy campaigns were also done there, and I had the privilege to be involved in some of these early experiments. Just a few details about our experiment. So we have a linear RF trap in which we store about 1,000 beryllium ions or so, and we laser cool them at 313 nanometers. And while the beryllium ions are being cooled, they scatter photons, which we can collect with the EMCCD camera, and we can actually image well, it's a crystal. It's a so-called Coulomb crystal of laser-cooled beryllium ions. And what we can do now is we can embed molecular ions in there, and we don't see them directly because they don't interact with this cooling laser, but they accumulate here at the core of the Coulomb crystal, and there is this dark band which allows us to tell that they are there and actually how many of them are there. And the molecular hydrogen ions cool to about 10 millikelvins or so. Now, with this, we can continue to do our spectroscopy. So we are interested in driving this vibrational transition with this near infrared laser. But to detect the transition, we use this dissociation laser, which will dissociate only the upper state population. So only if we were successfully driving this transition, molecules will be dissociated, and if they are dissociated, they are lost, and we can tell from these images that they are lost, and this is the way we get our signal, and this is called REMPD, Resonance Enhanced Multiphoton Dissociation Spectroscopy. Just to give you an example, maybe I can minimize this all together. Yep. I showed this before. We were interested in this transition, and if I scan the laser over this line, this is actually the line shape that we get, and these are megahertzes. And the line shape is rather irregular and broadened, and this is primarily because of the hyperfine structure. These are not degenerate levels. There's hyperfine splitting. That's because of the spins of the particles that are interacting. And I've indicated here different groups of transitions that you can retrieve here by the color coding. And in fact, each hyperfine transition is a stick because the line width is on the order of 10 Hertz. But because of the Doppler broadening, even at 10 millikelvin, everything melts together and you get this rather difficult to model line shape. Well, we managed to do it. And we managed in the end to determine this transition frequency, but with an uncertainty of about 1 parts per billion. And the theory is now approaching parts per trillion. So we really have to do something about it. And we need to deal in particular with the Doppler broadening. And this is why some 8 years ago, I came up with the idea to do 2-photon Doppler-free spectroscopy. And the idea is to do the following. We want to make this transition from vehicle 0 to vehicle 9 with 2 photons in a counter-propagating mode, such that it can be Doppler-free. And now these vibrational overtones are weak transitions by themselves, even if they are single photon. And 2-photon becomes even, well, it becomes very challenging unless you have a level somewhere halfway that can lead to a resonant enhancement of the 2-photon transition rate. And it turns out to be this vehicle 4 level. And we can address this 2-photon transition with nearly equal photon wavelengths. And it turns out that in an ion trap with a configuration like this, you end up in the Lamb-Dicker regime, which entirely removes your Doppler broadening. So that's great. So there was this paper that we published together with Lagrangian and Jean-Philippe to show that this is actually feasible with realistic experimental parameters. And it's not only the 2-photon signal that you expect, but there is also a Doppler broadened signal that follows from sequential excitation from vehicle 0 to vehicle 4. Then it stays here for a millisecond, and then you make the second step. And these are Doppler broadened transitions that also contribute to the signal. And Matthias German and Sejan Batra in my group, they did simulations showing that indeed you expect to see a Doppler broadened background, but also this narrow spike, which corresponds to the direct 2-photon signal, which can be very narrow. Well, in the meantime, we also upgraded our laser systems to reduce the laser line width, to hook it up to a full optical frequency measurement system. And it's great to be using the stuff that's available in Kjeld Eikema's lab, who is also in our group, because all of this allowed us to prepare to improve the uncertainty from the parts per billions to the parts per trillions. Just a few words about the target transitions that we look at, because there is this complication of all the hyperfine structure and different hyperfine transitions. And we will look at 2 lines, and that has to do with the strongest of the hyperfine interactions, namely that between the proton and the electron. The proton spin and the electron spin, they couple together to a resultant quantum or angular momentum F. And we will look at one hyperfine line with quantum number F equals 0 and one line with quantum number F equals 1. And in the spectrum that will look like this, these are the 2 lines that we will look at. But what we are really interested in is this position here, that's the transition or the position of the line that we would have had without any hyperfine structure. And it's basically the frequency of this transition. And this is the quantity of interest, because this is what's being calculated by Jean-Philippe and co-workers with 8 parts per trillion uncertainty. And this transition contains the information about the proton-electron mass ratio. Now, we don't have direct access to that. We only have access to the hyperfine frequencies. So what do? Well, we take theoretical hyperfine splittings, intervals, and we use those to correct our measurements to get the spin average frequency. And the nice thing is that we can measure this interval as well, and we can compare that with theory to ensure that theory is sufficiently in agreement with the measurement in order to do this. Here are a few experimental examples of the spectra that we obtained, and this really takes a long time to acquire these spectra. You're literally talking about months. And well, the nice thing is that we saw indeed a 2-photon Doppler-free signal with a line width and signal-to-noise ratio much as expected. And this really represents the first Doppler-free laser spectroscopy of the molecular hydrogen ion. And we can actually, well, for each line, we can determine the line center and then correct for systematic effects, leading to a total uncertainty on the optical transition of about 1 kilohertz, which translates to about 3 parts per trillion. Now, where does that put us on the map? Earlier, I showed this improvement in theoretical precision, and there have also been several experiments in Düsseldorf and also in our own group in Amsterdam. And well, although these measurements, they got quite some exposure in the literature, they were always trailing the theory in precision. Until very recently, there was a spectacular improvement reported by the Düsseldorf group, who have done Doppler-free terahertz spectroscopy of a rotational transition in HD+. And this is really the first time that theory and experiment are at about the same level. And we are here, even a bit further below. And this is really the first time now that an experiment is more precise than the theory. And we have entered deeply this regime where the uncertainties of physical constants are dominating, which implies that we can actually say something about their values. And at the same time also say something perhaps about 2 big issues in contemporary physics. Now, one big issue is the proton radius puzzle, and unfortunately I don't have time to discuss the whole history of this, so I'm assuming that everyone knows what I'm talking about. The situation currently is a bit confusing because until a few months ago, the status was solved according to Wikipedia. But if you now look at the list of unsolved problems in physics, the proton radius puzzle is back. So it's not entirely solved, apparently. And another issue is due to a new measurement that was done of the proton mass that was done at the Max Planck Institute in Heidelberg. And they found a value that differed from the co-data literature value by 3 sigma. It was smaller, so you may wonder what's going on. And these are effects that also have an impact on the theoretical predictions for HD+. Here, for example, you have the predicted vibrational transition frequency based on the theory of Jean-Philippe and Vladimir when you use co-data 14 constants. But if you replace the proton mass by the one that was measured at Heidelberg, at the Max Planck Institute, you end up somewhere here. That's almost a 3 sigma shift. And you also see it affects the theoretical error bar. And if you now also include the proton radius puzzle, you shift by almost 1 sigma. And well, fortunately, most of these issues were also recognized by the co-data and included in the latest adjustment. So, but now the question really is, where is our measurement in this chart? Well, it's here. And basically, our measurement is in agreement with these recent quote unquote anomalous measurements of the proton mass and the proton radius. I think it's also interesting to look at how this theoretical error bar, what that consists of. Well, the biggest contribution comes from the proton-electron mass ratio, even after the co-data 2018 adjustment. It's the biggest contributor. The theory has some intrinsical uncertainty, and you can see that there's also a relative modest contribution from the proton radius, the deuteron radius, and the Rydberg constant. And maybe this is not even that interesting. I think it's more interesting to show what, on this scale, what the effect of the proton radius puzzle is. And if you compare the old proton radius with the new one from ionic hydrogen spectroscopy, then in our case, that would translate into a 9 kilohertz shift. And it's HD plus, so we also have a deuteron, for which there was also a puzzle. And together they add up to 18 kilohertz, much bigger than any of the uncertainties in our theory and experiment. So why are we not very sensitive to that then? Well, there's also the Rydberg constant. And that is correlated to the proton radius and the deuteron radius. And it leads to a negative shift, and together the whole thing sums up to about 5 kilohertz, or about 1 sigma effect. And why is this? Well, there is this very precise 1s, 2s measurement from MPQ that was done in atomic hydrogen. And if you combine that with theory, you can find a constraint, something that constrains at the same time the proton radius and the Rydberg constant, and it's very tight. As you can see, if you change the value of the proton radius in whatever analysis you do, if you change the value of the proton radius, the Rydberg constant has to move along with it because it moves on a rail. And it's dictated by the 1s, 2s measurement. And this is also an explanation why this sensitivity to the proton radius puzzle in our case is not as big as you might initially hope for. Okay, so we have good agreement between our experiment and the latest theory value based on the co-data 18 constants, which take into account all the new latest measurements of the proton radius and the proton mass. And the question is, what conclusions can we draw? Now, typically in our field, also we ourselves, we claim the following. We say theory, including QED, was successfully tested. We adjust the value of the proton electron mass ratio then to match theory to experiment and get a new value of this constant. And in the same go, we use the good agreement between theory and experiment to put constraints on new physics, in our case specifically Yukawa type fifth forces. Now this test of the theory is essentially a hypothesis test where the theory is written as a function of several physical constants. And for simplicity, I'm going to assume that it depends only on the proton electron mass ratio. Now I can take also my experimental value and I can develop a test statistic, delta over sigma, where delta is basically the difference between theory and experiment divided by the combined uncertainty. And this is an equation that has 3 ingredients. And of these 3, we can only test 1. We have only 1 equation. So we have to make assumptions on the other 2 ingredients. Well, we're going to test theory, so we fix the proton electron mass ratio. That's one of the other ingredients. And we're going to assume that the experiment was done correctly. And thereby we fix also this one. And for the theory, we're going to allow for a possible deviation, and we're going to test whether that is there or not. So we write the theory as something as the theory value plus some unknown parameter zeta. Now, in a hypothesis test, you always have a null hypothesis that says that theory is correct or zeta is 0. And there's an alternative hypothesis where theory is incorrect and zeta is actually non-zero. And you may recall these kind of schematics where you have 2 columns that correspond to the different versions of reality. Well, we don't know which version of reality applies, but we can do a test, and the test will say something. And the test can say that the null hypothesis is true, and it can in fact be in agreement with reality, but there can also be errors, false positives, false negatives. And I really love these graphs. This doctor telling this man, sir, I've done a test and the test says you're pregnant. Well, this is obviously a type 1 error, right? And the same for this one here. There's actually 2 other aspects of hypothesis testing that are important, and those are the significance level alpha and the power of the test, 1 minus beta. Now, alpha and beta are the likelihoods of a type 1 or a type 2 error occurring. But another way of looking at them is depending on the outcome of the test. If the test says that the null hypothesis is accepted, then 1 minus alpha can be considered as the confidence level. And the same way, if your test outcome says that the alternative hypothesis is true, in that case, your confidence level is given by 1 minus beta. And to explain it a bit more in a bit more detail, and hopefully also a bit better to understand, I've made this animation, and what I have here is I have a distribution, this blue one, that is the distribution that corresponds to the null hypothesis, under which we assume that zeta is 0. So this distribution, which represents the distribution from which we drew this particular delta over sigma, is centered around 0. And through this significance level of alpha, which we set to 5%, we basically set threshold values at -2 sigma and +2 sigma. And if our value of delta over sigma, the difference between theory and experiment, if that's within these bounds, then we accept the null hypothesis. But if it's out of these bounds, then we accept the other hypothesis. And the alternative hypothesis has its own distribution, one where zeta is non-zero. And perhaps I don't know the value of zeta, but I can assume it has a certain value. I can, for example, assume it has 2 sigma. It's a 2 sigma effect. And then I can compute the confidence level, or the probability that given this distribution, I found a value that's out of these bounds. And that's shown here. That's the power of the test. That's about 50%. That's not a very high confidence level. And in fact, if I want to have a confidence level of 95%, I have to move all the way out to 3.6 sigma in order to achieve that. And for me, that was something, well, I guess I wasn't fully aware of that. You need a fairly large deviation from your theory to detect it with an acceptable confidence level. Now, so much for this hypothesis testing. Let's assume that, like in our case, we found agreement between theory and experiment. So we can accept the null hypothesis. We can make a claim that theory was successfully tested with the relative precision of sigma over f at a confidence level of 1 minus alpha, and we conclude that zeta is 0. We can also rule out, by the same token, certain effects zeta that are non-zero, because we haven't seen them. And so we can tell that they are not there. And the sensitivity depends actually on the confidence level that we set. What we cannot do is first use the test to conclude that zeta is 0, and then use this knowledge to adjust the proton-electron mass ratio to a new value. Because before we started doing the test, this was our theory expression. Then the test says zeta is 0. So now we have this expression here where we can adjust the proton-electron mass ratio. We make that variable now to make theory match with experiment. We can't do that because now we violate the assumptions of the test, where we assumed that the value of MP over ME is fixed. And if we do this, we basically invalidate the test, and we invalidate the conclusion that zeta is 0. So how can we then, well, oh yeah, so this is the title of a paper that we published some time ago. And with this knowledge, I guess we should reformulate the title of this article. So how do we then determine the proton-electron mass ratio? Well, we just assume the theory is correct. We don't do a test. Just forget about that. Just assume theory is correct and adjust the value. And this is also what CoData does. They don't do any testing. They just assume theory is correct. And what we furthermore do is, so we're going to constrain or adjust this value. For these parameters, we take the CoData 18 constant. And for MD over MP, we take a very precise recent measurement from the group of Ed Myers. And then we find a value of the proton mass or proton-electron mass ratio, which is in very good agreement with this smaller value that was found in Heidelberg. And the uncertainty that we achieve is 21 parts per trillion. And that's considerably more precise than the CoData value. It's also more precise than the Heidelberg measurement itself. And it's quite comparable to the very recent result achieved in Düsseldorf. And in fact, we can combine that one with our measurement. And then we get 18 parts per trillion combined uncertainty. And we do not enjoy the full square root of 2 improvement that you might hope for, because our measurement or our determination and that in Düsseldorf, they involve the same theory, and the theory errors turn out to be correlated. So that has a small effect here. Now, 2020 has been a horrible year in several respects, but it's also the year in which spectroscopy of HD+ at last surpassed the precision of ab initio theory. And it's the year wherein molecules confirm anomalies that were seen in measurements of single particles and atoms. And it's the year wherein molecular spectroscopy shows that it can provide particle mass ratios with a precision that's comparable to the very best panning trap measurements. Now, as a short outlook, just a few words about fifth forces. In 2013, we published a paper where we proposed that molecules might be sensitive to a Yukawa type fifth force, which is basically a modification to the Coulomb interaction, and is a force acting between the nuclei. And it's a force that assumes massive force carriers, so the force has a limited range. And if this range falls, well, if it's more or less equal to the size of the molecule, and if this coupling constant is large enough, we might see a shift in our transitions with respect to the theory. And if you don't see such a shift, then you can constrain the fifth force. And this is what we do. I'd like to remind you of the fact that if you constrain a force, you're considering the alternative hypothesis for which you must use the power of the test. And for a 95% confidence level, we must use this 3.6 sigma threshold and not the 2 sigma, which we specified earlier. So previous HD+ constraints were a bit over-constraining for that matter. And we developed a refined method that can combine multiple constraints into one constraint. And what I mean by that is the following. Here you see an example of a constraint of the coupling constant of the fifth force and versus the range of the fifth force. And the Düsseldorf group published this orange curve in their paper. This now is corrected for this 3.6 sigma. And we, from our measurement, can derive a similar constraint, which is slightly more constraining at large range, perhaps. And with this new method, we can combine these into this green curve, and then everything above the green curve is ruled out by our measurements, but there could still be a fifth force hiding somewhere here. Now, with that, I'd like to conclude. Thank you all for your presence and your attention.
Good afternoon, everyone. First, I would like to thank Stefan, Christian, and Klaus, both for giving us this opportunity to give this talk and for setting up this series of seminars. This is really a great initiative. And so, as was announced by Jeroen, I will tell you about the theoretical side of the story. And I will introduce you to the methods we use to calculate the energy level of molecular hydrogen ions. And what I will present today is the result of a work that started roughly 2 decades ago. And this work was started by a single person, Vladimir Korobov, from the Joint Institute for Nuclear Research in Dubna. And several years later, Laurent Hélico and I joined efforts with him. And I would like to thank him very warmly for these years of work together. And of course, his role in what I will present today has been essential. Many thanks also, of course, to the Jeroen and the whole Amsterdam team for the fruitful and friendly collaboration. Mohammad Haidar is my PhD student, and he worked on estimating some systematic effects in the Amsterdam experiment. And more recently, we worked on another aspect of the theory, which I will briefly describe at the end of my talk, in collaboration also with Zhenxiang Zhong from Wuhan. And finally, although it's not today's topic. I take the opportunity to present the experimental team at LKB, led by Laurent, working on spectroscopy of H2+. Okay, now as an introduction, I would like to mention that these calculations belong to a wider field of bound state QED calculations in light few-body systems related to precision laser spectroscopy experiments. This is a very active field as many high-resolution spectroscopy projects are ongoing in the hydrogen atom, helium plus ion, positronium, muonium, helium and antiprotonic helium, neutral hydrogen molecules, and so on. These projects have various aims related to fundamental constants, tests of fundamental symmetries, probing for physics beyond the standard model, or the determination of nuclear radii. Among these systems, the one where the theory was pushed to the highest level of accuracy is, of course, the simplest one, the hydrogen atom, where QED corrections have been developed for more than 70 years. And so it's clear that the hydrogen atom theory is an essential point of reference for this field and for our work in particular. In the next few slides, I'm going to briefly describe the theoretical approach we have used to calculate QED corrections. QED is a relativistic theory, and so for a one-body problem, such as the bound electron in a hydrogen atom in the so-called external field approximation, the natural starting point is the Dirac equation. However, Dirac's equation is a one-particle equation, and for two-body systems, a more elaborate approach is required based on the Bethe-Salpeter equation. And to extend such an approach to three-body systems would be extremely complex. And that's why we follow an alternative approach called non-relativistic quantum electrodynamics, in brief NRQED, which is very widely used for weakly bound few-body systems. In this approach, the problem is reformulated in a non-relativistic framework using the Schrödinger wave functions. And so in this the first step is to derive from QED the NRQED Lagrangian of interaction between an electron and the electromagnetic field. And then one applies the non-relativistic perturbation theory to derive an effective Hamiltonian at the desired order, which can then be evaluated numerically. And this is what the NRQED Lagrangian looks like. It takes the form of an expansion in powers of the fields, the E and B fields, as well as the scalar potential A0 and the vector potential A. And you can also see this expansion as corresponding to an expansion in powers of V over C, where V is a particle's velocity. This Lagrangian so can be constructed ab initio by writing down all the terms satisfying the required symmetries. And then the coefficients, CF, CD, CS, and so on, are fixed by a matching procedure, imposing that the NRQED and QED scattering amplitudes coincide to the desired order in alpha. And finally, for the theory to be complete, one needs to include also contact interaction terms to account for processes that involve relativistic momenta of the order of the electron mass. Next step is to apply the non-relativistic perturbation theory, which can be formalized in terms of Feynman diagrams, similarly to QED. Here are a few examples of some NRQED interaction vertices. They are more numerous than in QED because each term of the NRQED Lagrangian gives rise to a different vertex. But each diagram will be significantly simpler to calculate than the QED ones. And finally, I need to explain the scheme by which QED corrections are classified. As you know, QED corrections are obtained in a perturbative expansion in powers of the fine structure constant alpha. But in NRQED, we are also treating perturbatively the binding potential, and that's why NRQED is often called perturbative methods, as opposed to non-perturbative methods where only the alpha expansion is done. And so, since V over C for an electron is of order Z alpha in an atom or molecule, where Z is the charge of the nucleus, or Z alpha small m over big M for a nucleus. This means that NRQED is in fact an expansion in powers of 3 small parameters, alpha, Z alpha, and M over M. And this leads to the following classification of corrections. The pure relativistic corrections, which depend only on Z alpha, radiative corrections, which also depend on alpha, recoil corrections, depending on the mass ratio, and finally, radiative recoil corrections, depending on all 3 parameters. And so now we are ready to turn to HD+. And this is our theoretical prediction for the V equals 0 to 9 transition in HD+, which was measured in Amsterdam in units of kilohertz. And this is based on the theory we presented in this paper from 2017. For these values, we have used the CODATA 2018 values of the fundamental constants. The first line is the non-relativistic transition frequency, and the next lines are the QED corrections in growing order of alpha. With respect to the classification I showed in the previous slide, I gathered in each line different terms which can have different powers of alpha and Z alpha and M over M, but with the same total power of alpha. The uncertainty I give here, 3.1 kilohertz, is only the theoretical uncertainty of the calculation. As Jeroen discussed already, there is also an uncertainty coming from the values of the fundamental constants. And now in the next slides, I will browse through the calculations involved by each line of this table. And in doing so, I will try to highlight the points which are specific to the molecular nature of the system, both in the methods and in the correction terms themselves. Okay, so the first task is to solve the non-relativistic 3-body problem for our system, composed of a deuteron, a proton, and an electron. And one of the first things we learn in a molecular physics course is that we can perform the Born-Oppenheimer approximation, which consists in separating the electronic and nuclear degrees of freedom. So in the first step, one solves the Schrödinger equation for the electron in the field of 2 fixed nuclei for a given internuclear distance r. This problem is often used in textbooks to introduce the variational method, usually in its simplest form, which is the LCAO approximation, where the electronic wave function is written as a linear combination of 1s atomic orbitals. Of course, this approach is far from being precise enough, and whenever we use the adiabatic approximation, we use a more sophisticated variational expansion in terms of real exponentials of the electron nucleus distances with exponents which are chosen in a pseudo-random way in optimized intervals. This method was developed by Vladimir in this paper. And it yields very high accuracies. To give you an idea, we typically obtain 20 digits of accuracy with around 100 terms in this expansion. And on this figure, I compare the LCO wave function to the exact one at the equilibrium bond length of 2 atomic units. And the point I want to make here is just that the LCO approximation is not that bad. And this already tells us that the largest QED correction terms, which depend on the electronic wave function, will have similar magnitude as compared to the hydrogen atom case. And so in that sense, we can say that the theory of HD+ is strongly correlated to the theory of the hydrogen atom. However, there are also some smaller corrections which depend on the vibrational part of the wave function and which behave differently. And I will show a few examples of such terms a bit later. Now, coming back to the adiabatic approximation, it's well known that it yields an accuracy of order small m over big M, which is obviously insufficient for our needs. It's perfectly possible to improve this by including non-adiabatic corrections in a perturbative scheme. But in order to reach sufficient accuracy, we would need to consider quite high orders of perturbation, and this would be very tedious. And therefore, we rely on non-adiabatic calculations for the non-relativistic energy, at least, and for leading corrections. And we use the adiabatic approximation only for small terms, such that this m over m accuracy level will be enough for our precision goal. So the variational methods we use for the three-body problem has been developed by Vladimir Korobov, and clearly it's one of our essential tools to reach these highly accurate predictions. First, there is a separation between radial and angular variables, which uses angular functions called bipolar spherical harmonics. And then the radial wave functions are expanded in a basis of correlated complex exponentials. The exponents are again chosen in a pseudo-random way in optimized intervals. And we use real exponents for the electronic variables, R1 and R2, so similarly to the Born-Oppenheimer calculations. But we use complex exponents for the internuclear variable, which is important to reproduce the oscillatory behavior of the vibrational wave functions, as illustrated here by a few examples. This method allows us to reach quite high accuracies with reasonable numerical means. For example, this calculation from the year 2000 yielded 18 digits with a basis size of 2200, and this only requires a few minutes on a single CPU core. Of course, it's not the only possible method, and other authors have also obtained very high accuracies, as you can see in this selection of results. And the precision has even been pushed as far as 34 digits in the last line, which triggers the question, what level of precision is actually required? You might think that, okay, if we need 10 to minus 12 accuracy in the end, for example, then we need at least 10 to minus 12 or better on the non-relativistic energy. But in fact, we need more because we don't use only the non-relativistic energy, but also the non-relativistic wave function in order to calculate the leading order corrections by perturbation theory. And in variational calculations, as a rule of thumb, the accuracy of the wave function is typically the square root of the energy accuracy. And so one can estimate that an accuracy of 10 to minus 18, roughly, on the energy is required to have sufficient accuracy on the largest correction terms. But this is achieved without any problems with our variational method. And so that we are never limited by problems of numerical accuracy. And now we begin our survey of relativistic and QED corrections, beginning with the leading order relativistic corrections at M alpha 4 order. So in this case, the effective Hamiltonian is well known. It's the Breit.Pauli Hamiltonian. All the required expectation values have been recently recalculated with a very high accuracy of 11 digits in this paper. And I've written down here all the contributions. Don't worry, I won't do that again at the higher orders because the number of terms explodes. But here, what I want to show is how different terms have different behaviors. First, look at the relativistic corrections for the electron. So this term depends on the electronic part of the wave function. And as a result, it has a weak dependence on the vibrational quantum state of the order of a few percent per quantum of vibration. And the similar is true for the transverse photon exchange term between the electron and the nuclei. But the third term, which is the transverse photon exchange between the nuclei, is the first example of a term which obviously would not exist in an atom, and that we could call a specifically molecular term. And this one depends on the vibrational part of the wave function. And as you can see from this plot, it has a much stronger dependence on the vibrational state. The next terms are the leading order shift induced by the finite size of the nuclei, and as well as the nuclear Darwin term. And again, both terms depend on the electronic part of the wave function, and they only weakly depend on the vibrational state. But the last term, which is the nuclear kinetic correction, although it does not differ in nature from the atomic case, where you also have similar P4 terms, the fact that it depends on the nuclear momentum, again, leads to a strong dependence on the vibrational state. At the following order, M alpha to the 5, we find the leading order radiative corrections, such as the self-energy or the vacuum polarization. And the largest contribution is the self-energy, which was the key ingredient to interpret the original Lamp-Shift experiment from 1947. And this includes the beta logarithm which is well known to be a difficult quantity to evaluate numerically. It is often written under this form as a sum over intermediate state. And the difficulty of the calculation stems from the fact that the dominant contribution comes from scattering state lying high in the continuum. And this sum converges very slowly as a function of the highest energy included in the basis set. And Vladimir Korobov developed a very efficient scheme to calculate this beta logarithm. And 8 to 9 digits of accuracy were obtained, which can be considered as a big achievement for such a three-body system. And so I am giving these numbers because I think that among all our calculations, they are certainly the hardest numbers to get from a purely numerical point of view, especially for the V equal 9 level, which required a basis set with 25,000 functions and a computation time of about 1 month. Let's move on to the M alpha 6 order. One important point here is that many corrections, including, for example, the one loop self-energy written here, are so-called state independent. And in the NRQED approach, such corrections appear in the form of contact terms with a known coefficient, which can be calculated by scattering QED calculation, multiplied by the square root of the wave function at the electron nucleus coalescence point. And such terms don't require any new calculation. The only term at this order which requires an independent calculation is the pure relativistic correction to the electron, which was calculated by Vladimir in the adiabatic approximation. So the corresponding effective Hamiltonian H6 can be derived using NRQED. And then perturbation theory tells us that the total energy shift is a sum of two terms, the expectation value of H6 plus the effect of the leading order Breit.Pauli Hamiltonian at the second order of perturbation theory. And this yields a correction curve as a function of internuclear distance r, which can then be averaged over the vibrational wave functions. However, this is not the end of the story, as we realized a few years ago, originating from a remark by Jeroen, by the way, because the second order contribution, as written here, only takes into account the perturbation of the electronic part of the wave function. However, the relativistic corrections shift the electronic Born-Oppenheimer curve, and as a result, indirectly, they also affect the vibrational wave functions. And this gives rise to this vibrational contribution, which is another example of those terms which we can call specifically molecular. And again, you see that this part depends more strongly on the vibrational state. At this order, we also partially evaluated the recoil and radiative recoil correction at the first order in the mass ratio. Both terms include a state-independent part, which we take from the literature, and this does not require any new calculations, as I already said. But the pure recoil part has a state-dependent contribution, which we roughly estimate using the LCAO approximation, which means that we use the known coefficient obtained for the 1s state of hydrogen. And then we estimate our error bar as equal to this state-dependent part. I should also mention that a calculation of the M-alpha-6 order relativistic corrections, including the recoil terms, in an exact three-body approach is under consideration by Zheng Zhang and his collaborators, who recently derived an effective Hamiltonian for these corrections. Next comes the M-alpha-7 order. Here, there were two contributions that required new calculations, the one-loop self-energy and the vacuum polarization. In this case, the NRQED effective Hamiltonian was already available from the literature, but it did not include the contact terms. And on the other hand, a full calculation for the 1s state of hydrogen had been done, and this allowed us to construct the complete effective Hamiltonian. And apart from this analytical work, we also had to solve numerical problems in the low energy part, which is a set of relativistic corrections to the beta logarithm and poses similar numerical difficulties. The vacuum polarization part was easier, and we were able to calculate it both in the adiabatic and three-body approaches, which allowed us to check the accuracy of the adiabatic approach. Last but not least, the M-alpha-8 order. Here, the two main terms are the two-loop corrections and the one-loop self-energy. For the two-loop corrections, again, we used the NRQED effective Hamiltonian from the same 2005 paper I cited in the previous slide. And this allowed us to calculate the logarithmic contribution, B61, 62, 63. But the non-logarithmic part, B60, poses very difficult problems, and it has not been completely evaluated yet, even in the hydrogen atom. So we just estimated this term in the LCO approximation using the estimate done for the 1s state from the literature. And we estimate our uncertainty as the total value of this term. And in the one-loop self-energy, finally, the logarithmic term A71 is known, but the A70 term is yet uncalculated, even in hydrogen. And again, we estimate it in the LCO approximation and estimate our error bar as equal to the total value of this term. And this is our main theoretical uncertainty at present. So we have finished our survey of QED corrections. And now, as you have heard from Jeroen, the experimental accuracy has surpassed the theoretical one by about a factor of 3, which is, of course, a great motivation to improve the theory further. Presently, our uncertainty, as I told you, is mainly limited by two uncalculated terms at the M-alpha-8 order, one in the one-loop self-energy and another one in the two-loop corrections. And so it's clear that the next step will be to improve the one-loop self-energy. How should we do that? One possibility is to follow the way opened by the hydrogen atom calculations, where this contribution was calculated very accurately using a non-perturbative approach. But to do this, we should first be able to solve the Dirac equation for an electron in a two-center potential with very high accuracy, and this is by no means easy. But if we manage to calculate this term, we can estimate that the theoretical error bar would come roughly to the same level as the present experimental accuracy. Okay, finally, to end my talk, I would like to say just a few words about our latest work, which is on the hyperfine structure of hydrogen molecular ions and Hd+ in particular. Here also, it's interesting to improve the theory, since the recent progress of experiments, not only in Amsterdam, but also in Stefan Schiller's group, on the rotational transition. This allows for the first time to make a high precision comparison of the hyperfine structure with the theory. And an interesting perspective would be to use HD+ spectroscopy to improve the determination of the deuterium quadrupole moment. The present status is that all the coefficients of the hyperfine Hamiltonian have been calculated at the leading order. And we need now to calculate higher order corrections to the largest coefficients. For the largest one, which is the spin-spin Fermi contact interaction terms, E4 and E5, this is already done. And we applied these calculations to the case of H2+, where we obtained excellent agreement with experiments at the level of 1 ppm. And now we are working on the next largest coefficients, E1, E6, E7, so the spin orbit and the tensor interactions. And we recently put on archive the derivation of the effective Hamiltonian for these corrections, and along with first numerical results, and more complete numerical results and comparison with experiments will come soon, so stay tuned. And with that, I will stop here, and thank you all for your attention.